We have this row on.
Oh, for some reason we are live already. I didn't even realize we are. Okay, for some reason we are live already. I don't have the option of starting later and all. If you want later, I will clip the.
Disclaimer for the stock. The only reason you are going to clip this out.
Wait. Since you are anyway.
No, I can't there.
No. So that Prahladh is.
You want to record and show it?
No. His disclaimer. I mean, the one that he didn't want to record.
I gave this talk exactly a month ago in Delhi, and I had flights ready for it. So I thought I need back this ROI from having made flight. So, Prabhu, there was a free slot. I agreed to the talk. Last night at 11:30 p.m., put my laptop and I realized I don't see the file with the slides. And there are. Till now, I have no clue what happened to those slides. Those are missing for me. But frantically this morning, I had to take one of my all the slides and modify them this morning. So these are not, even those, the previous slides are a modification. But I spent a week modifying them. Here I spent 2 hours in the morning modifying the slides. There's something called Dropbox. So I go on OneDrive. Then OneDrive, go and complain to Nadella. No, OneDrive. So I seem to have deleted it. There's a backup. OneDrive has backup of 30 days. And there's exactly equivalent. So I have things from 29th July. I gave the talk on 28th July. That's it. I just have to
You should also add that the last time I was in a talk by Prahladh, I think half an hour before the talk, he realized that he was supposed to talk for 3 hours and not to 1 hour or something. I mean,
Okay, welcome everyone. A few weeks back, Madhusudan was here, and he said that he's competing with Prahladh for being the most frequent visitor to the department. So this talk is in the same spirit. We had a talk by Madhu, so now due to that competition, he is going to speak. So that's why we are here.
Thanks. Yeah, as I mentioned, there's a talk which I recently given, so I thought I'd give it. I've given it at other places, so I thought I might as well give it here back in at home. 6 here. Oh, sorry. There's 6 here. Easily escape. So this is not in my prime area. So this is actually a talk which has more crypto connections than one, but it's a connection between PCPs and crypto. It came about in conversations with several people working in cryptography and asking how much of PCPs do we really need for some of the cryptographic applications. The large part of my talk, what I will do is actually motivate the setting. A considerable part of the talk will be motivating the setting, the notion of proof systems, what are these applications to cryptography, hardness of approximation, and we want certain better applications in cryptography, and we'll ask what do we really need of these proof systems in order to get these better applications, and go to that particular question and then try to answer it completely. Okay. So, in trying to answer that question, we'll define a new kind of proof system which we refer to, for the lack of imagination, as dot product proofs. You'll see why it's called dot product proofs. And in fact, I'll give you almost a full construction of these dot product proofs and a couple of applications of dot product. Okay, and if you can feel free to stop me, and at any point of time, I would be happy if I even just finish this part of the talk.
This is the 1 hour talk.
Happy if it was 20 minutes or so. Yeah. Okay. So many of you know that there are these amazing objects called probabilistically checkable proofs. So what are these objects? So this was the PCP theorem was proved in the early 90s by Safra, Arora, Sudan and Sekedi, and they showed that anything that can be checked in the classical NP sense, any proof that can be checked by looking at the whole proof can be rewritten in a different format, so that the new checking process is randomized, unlike deterministic. You don't look at the whole proof, you just look at a few bits. But the key thing is you can just look at a few locations in the proof and be convinced that the proof is correct. That is, you have an n bit, you want to check if a graph is three-colorable or not. The usual thing is you go over the proof is typically the three coloring of the graph. You go over every edge of the graph and check if the two endpoints are different. It's conceivable. Suppose I manage to give a reduction from this graph to another graph, so that the original graph was three-colorable, the new graph is also three-colorable. If the original graph is not three-colorable, then any three-coloring will violate, say, at least 1% of the edges. Now you don't have to read all this one. You just pick a random edge at this one, check if the two endpoints are different. In the yes case, of course, you will be able to check if there's a coloring with probability 1. In the no case, the fact that you will pass the test is only 99%, because 1% of the time, no matter which coloring you give there, you will always find the two edges endpoints are the same. So PCP theorem gave us this remarkable way of rewriting proofs which had this feature, and this has had numerous applications. One major source of application, or major area of applications of PCP theorems is towards hardness of approximation. That's sort of proving stronger and stronger negative results. They have also been very poor. It also has applications towards cryptography, in which we are able to get better proof systems. So I'll talk about both these now. Let's go to the applications towards hardness of approximation. An immediate consequence of this fact is the fact that max 3 sat. That is, I give you a 3 sat aside instance, something of this form, and I ask you to find a setting of the variables that satisfies the most number of clauses. This is an NP complete problem. We don't expect to solve this unless NP equal to P. What the PCP theorem says is it's not just hard to solve it, it's also hard to approximate it. That is, the fact that this 99% which I mentioned here will exactly translate to another number, possibly 99.99%, but some number which is bounded away from 1. It will say that max 3 set is NP hard to approximate. This is almost an immediate consequence of the PCP theorem. And here I just mean this is the consequence is just 0.99. A gap here will imply a gap there, and this is exactly where I'm going to give a reduction. This is done by reduction. It's a reduction from the classical 3-sat problem to the gap 3-sat problem. A 3-sat problem in which in the yes case there is an assignment. In the no case, no assignment will satisfy more than 99% of the clauses. Okay. So this is great. The PCP theorem gives us this reduction. What I would now want, and in fact, it's not hard to see that this statement is equivalent to the PCP theorem. You can go back. These are actually equivalent statements.
So sorry, what is the gap problem again?
The gap, so the usual max-sat problem is to find, given a 3-sat instance, to find if it is satisfiable or not satisfiable. That is, every assignment will violate at least one clause. Now I promise you that in the yes case, there is a satisfying assignment. In the no case, I guarantee that every assignment at least violates 1% of the clauses. So there's a gap between, that is this one. This supposedly is an easier problem to solve, but what stating is no, it's not any easier, it's the same. If you can solve this, you can solve the original problem. That's what in PCP theorem is just a reduction between the classical 3-sat problem and this gap version of the problem. It can be just viewed as a reduction. And it's a polynomial type reduction. And it's important to notice for what I'm going to now say, it's polynomial time. And in fact, the reduction is the best known polynomial. The original proof of the PCP theorem, I think the polynomial was something like n cube or something, n cube or n power 5. And today we know that it is n polylog n. We can make it as small as n polylog n. In fact, the exponent over log is also a nice, it's like 5 or something.
This is the running time of the.
This is the running time of the reduction. It's also the size of the target reduction. If this was on n variables, this will be on n polylog n variables. Now, people now study not just assumption NP not equal to P. They would like to know NP not equal to C will say that the approximation problem, there is no polynomial time algorithm assuming NP is not equal to P. But people also now study ETH hardness. What is ETH hardness? ETH hardness is stating that 3-SAT is not just NP complete, it doesn't have polynomial time. In fact, it is actually requires strictly exponential time. That exponential time hypothesis. So suppose you assume the exponential time hypothesis for 3-SAT. This is a strongly believed assumption that 3-SAT, in fact, any algorithm for 3-SAT requires exponential amount of time. Can we prove the corresponding gap version of 3-SAT? That is, the corresponding gap problem which I just mentioned, that also will require exponential amount of time. Can we prove the same result? Does the PCP theorem give you this? If you assume 3-SAT is not in P, this reduction will tell you that gap 3-SAT is also not in P. Because if gap 3-SAT had been in P, you could have done this reduction and got 3-SAT is in P. Let's ask if the same thing works for ETH. If suppose you assume that gap 3-SAT doesn't have exponential time algorithms, does it combined with the PCP theorem tell you that the gap 3-SAT problem does not have exponential time? Unfortunately, it does not, because you're moving an instance from n to n polylog n. Therefore, you will get this only if the PCP is of linear size. If the PCP were of linear size, strictly linear, order n, not order n, that extra polylog n is the troublesome factor here. So we don't know this. We don't know this translation from ETH to gap ETH. Here we knew gap SAT and gap SAT were both the same problem. They are of equivalent hardness. Here we don't know. So if you want to assume the approximation version is hard in the exponential sense, we have to make a new assumption here, gap ETH. And the question is, can we strengthen the PCP theorem in order to prove gap ETH? That's one of our things. It's a long-standing open problem. Can we improve the PCP theorem either by the PCP theorem or other means to move from the ETH assumption to the gap ETH assumption? The gap ETH assumption is a stronger assumption. Do I know how much stronger is it over the ETH assumption? Question so far? And the reason the PCP theorem does not imply it is because we don't have linear size PCPs. All known proofs of the PCP theorem give you that the reduction from 3-SAT to gap 3-SAT requires at least an extra logarithmic overhead. Okay? So what we will yeah.
And ETH hardness is a stronger assumption than NP hardness.
Yes.
So then you would expect a better hardness result over there. Like what? So right now we already know that max-LIN is NP hard to approximate to 0.99 or whatever.
No. The point is certain. If you prove that 3-SAT is not in P, you will get that 3-SAT gap 3-SAT is not in P. If you assume 3-SAT is not, if you assume the ETH assumption, what you will get is gap 3-SAT requires
2 to the n by polylog or something. 2
to the n by polylog. You won't get that it requires strictly exponential time. You only get that. I want to say gap 3-SAT also requires 2 to the n. Because I'm strengthening both the hypothesis and the conclusion.
Yeah.
So it's not clear you will get it. So you will get a stronger conclusion than what you had before. But whether you get this conclusion is we don't know how to do that. And that one way of getting it is we had linear. If the PCP theorem, we had a proof of the PCP theorem in which the PCP is constructed a linear size, then we could do this. So what we'll see by the end.
Is or no?
I don't know. It's unclear. One might be able to prove this without doing this. Yeah, I don't know. So what we will prove in this, we take a related problem, MAX-LIN. But the key thing is it's not max 3 lin. Max-LIN, I'm going to allow arbitrary arity. but still over say GF2 or GF3 of small fixed finite field, I look at this problem and ask what's the maximum number of equations that you can solve in this. Max-3-Lin is known. Gap Max-3-Lin, the reduction, the standard PCP theorem works. What we'll show is if we weaken this from 3 to an arbitrary arity, we can actually show that it is ETH hard to show Max-Lin. That's going to be one. We are giving up locality, which is a big thing for PCP theorem. That is Max-3 sat, Max-3-Lin. The key thing out there was locality. We're going to give up on that. If we give up on that, we want to show that we can actually prove the hardness of this version of the problem. Okay.
What is the version here does not talk anything about arity.
It doesn't talk anything about arity. In some sense,
it could be non-constant. Like
in fact, it will be non-constant arity.
Like max sat.
Because if you get it for constant arity, I would have proved
Right.
ETH implies a gap ETH, because that would immediately give you this. We don't prove it. So in some sense, what can be seen as this talk is, on the other hand, I don't know how. For some CSPs, having large arity makes the underlying problem meaningless. For example, if I put an arbitrary CSP, I could just put one big circuit of size n there. So there's no gap. Trivially, I get a 1 versus 0 gap. It is certain specific CSPs like MAX-LIN, like CNF constraints or LIN constraints for which the gap version still makes sense. Okay. Otherwise, you need to have the locality in the definition. So in some sense, you could say this is a meaningless problem to consider because I've expanded the arity. In other words, I'm not proving the full-fledged theorem, I'm proving a weaker theorem, and we're showing that if we relax the arity assumption, then in fact we can show the hardness of this.
But this will not hold for say max K factor, you're tending like letting K to prove.
I don't know how to prove it. It might be true. It might be our proof might also be able to give it for max K set. I don't know. Our results won't fetch. Okay. So this is towards the improving the state of art in the hardness of approximation here. Let's go to the positive outcomes of PCPs. This is their application.
This word, so you still need this. I mean, what did your slide say? You still need a linear size PCP?
No. We will give you a full proof of this fact bypassing the linear size PCPs.
Okay.
By the end of this talk, you will. I would have proved Max-LIN is NP hard to approximate
Without using.
a gap Max-LIN is NP hard to approximate without using the. Yeah. In fact, we will completely bypass the PCP theorem to prove this. Let's look at those were one set of applications of the PCP theorem. Want to look at another set of applications. These are applications to cryptographic proof systems. So one thing PCPs have been used for is for sustained argument. That is, somebody has done a huge computation or some task, and they want to convince you that they have done the task. So they're going to have a conversation with you. One way is, of course, they can show you the entire computation tableau and say, look at it, I have done the task. But then by reading the entire computation tableau, you're basically going over the entire computation tableau and you're spending as much time as the other person did to do the task. So you would like to have, so there is suppose there's a powerful person whom you have delegated the task to. Say you asked the AWS or something to do a task to you, and you want them to convince that they have actually done the task, but you're willing to have a conversation back and forth with them at the end of this, and so that they can convince you that they have done the task correctly. And PCPs actually gave you a means of doing this, and this was actually the succinct arguments of Killian and Mikali. They just said the server who has done the task writes the whole task, the proof that they have done it in a PCP format, and then you query it in a few locations. Now, querying is what? You can't query and interact, because once you see the first question, you know what is the second question, you know what the second thing, and you can change the answer. Therefore, you have to, that's why some crypto comes into the picture. So let's see what happens over here. So what they do is, suppose this was the proof. You don't need to go into details of the proof. Let me tell you. So one second. So how do these succinct arguments work? There's a server which has completed a task, and you want to know that the task has been done. So what they want to show you, actually give you, is a PCP of the whole. They have a proof that they have done the task. They are not going to give you the proof. They're going to give you a PCP of the proof. And if they give you the entire PCP, Then there's a the communication is very large. In fact, PCP is usually longer than the original NP statement. In fact, right now all PCPs at least a logarithmic overhead. You want to have only a short communication with them. You don't want to have a long communication. So you could say, I don't want them to give me a PCP. I want to just give them, I'll ask them a particular set of questions and ask only the answers to these questions in the proof. But if they have not committed to the proof, and they get to know the questions, they can give the answers in such a way that they're too cheap. So you want to ensure that they commit to the proof when you ask the question. So the proof should be written on stone without revealing it to it, and that's what this one does. You have this whole proof, you sort of commit in some way. This is a commitment way of committing to the entire proof in some way. Forget about how this one is done using Merkle-Tree construction. So the first step will be the server who has done the task for you will construct the PCP. And then they will commit to the PCP and they'll give you a small commitment to you and say, once you have this commitment, they more or less can't change the proof. And then you will then say, I want to now read, say, the fourth bit. Then, if you want to read the fourth bit, they'll reveal all the things along this path to show you that that fourth bit is actually truthful to what this commitment is. Now, you want to read another thing, they'll give you another path from the root to the leaf. So, this is how it works. It's low communication, but yet all the task is done by the server side. So typically they will
also give the siblings, right?
They also give the siblings. You have to show that pi4 is correct. You have to give all the siblings along the path, but it's only a logarithmic over here. So the way it's hammered, there's a witness. They construct a PCP encoding of the witness, and then there's a cryptographic hash of it. Succincted. This is how all succinct arguments have been in practice so far. And this seems like a very heavy hammer. Firstly, you're doing a full-fledged PCP and a cryptographic hash. This one. On one hand, this is a computationally heavy task, PCP theorem. And the other one, it's unclear. Right now, notice it, because you have to give the whole path, you have to give a logarithmic amount of bits. Whether you can commit to it even smaller number of bits, much smaller than logarithmic. Can you commit with smaller number of bits, just larger than the security parameter? Not logarithmic in the length of the proof, would like to ask. So it's not known whether you require logarithmic min. So that was the quest in cryptographic application. They wanted to know, is there a way to come up with succinct arguments bypassing this heavy hammer of PCPs that will remove the computationally intensive part of it and also have a more succinct than what is done by the Merkle-Tree construction. This was asked in the crypto community. And there have been several attempts to this. This has been a long, since the mid-90s, there have been a lot of effort to it. One was because you're anyhow having an interaction back and forth. That you don't have to work with the honest-to-God PCP, you can work with what I call these interactive PCPs. This is what was introduced by Kalai and Raz 2008. So it commits to a PCP in the first round, then another PCP in the second round, and you go back and forth. It's not a single proof, there are multiple proofs, and they were able to show something over here. So this gave a whole, this was the proof systems based on them by Elie Ben-Sasson, Alexandre Chessia, and Spooner. They constructed these sort of succinct arguments which are actually used in practice. So several of the proof systems that run in practice, which check things on the blockchain like Ligero, Aurora, Fry, Star, all actually use this interactive PCPs over it. Only catch is they are still use the PCP machinery, so they are a bit intensive. The Kalai managed to give this, but they were not successful. They avoided get around succinct, and then there was subsequent work which showed that you could actually get linear time provers in this context, but they were still not succinct.
So maybe you're confused with how this is going to happen. So there is a prover that is trying to convince you that the task has been completed correctly.
Yeah.
And you are trying to verify
the
And every step the prover sends you a message in a PCP form.
No, you cannot. The message, you are also going to be charged for the length of the message. The communication has to be short. If they can start the entire message, they could have done it right away. Could have just sent the PCP.
That was my going to be.
Could have done.
But what instead?
So instead of that, what they use is they use the fact that Kalai Raz build this thing in which each time they send a PCP. Over that they send a commitment in each case. The Kalai Raz just built an interactive PCP. And these proof systems do a sort of commitment over the PCPs to do this. But these are where, now that you have communication, you can do it. But these inherently needed log grounds of communication to go through. This was a way to get around it. I'm not going to go into the details. We'll bypass all of this one. But these things are still not succinct because there was a commitment at each step, and the way you had to do it was actually doing the Merkle tree over it.
So what is the point there? Because even before you had a log depth tree, here you also have a log depth tree.
You were able to construct provers which were linear time. It didn't have this n polylog.
Versus n polylog. Okay.
Yeah. So now the point is, there's a server trying to do extra work to convince you. Question is, the extra work that they're doing to convince you seems to be more work than the original task itself. So you want the overhead to be as minimal as possible, to be only linear, not n polylog n. So current PCPs are bad because of that extra, because they are blow up the verification part seems to be more intensive than the original task. You want the PCPs to be nearly linear length or even smaller. And what these new things allowed is for basically doing that.
For exactly.
They managed to get linear time. Yeah. Okay. But they didn't get the succinctness because they still had to do the Merkle tree over this. An alternate, this one was suggested. I will not go into mechanism of this, but it will lead to our definition eventually. Was something introduced by Yuval Ishai, Kushlevitz, and Ostrowski in 2007. They introduced a different query mechanism into the PCP, which is called linear PCPs. What are linear PCPs? Let's first define that. In the sense that previously, how did a PCP work? You check the PCP by querying locations into the one. You said, I want to look at the 4th bit, I want to look at the 5th bit, I want to look at the 100th bit. What now? I'm going to change the query mechanism. In the sense, I'll say, I have this particular, you view the proof as a vector over some finite field. So here, say a finite field over GF7, say, all things. And you come up with, now the queries are no longer single locations, but the queries themselves are also vectors. And what you ask is the dot product or the inner product of these Q1s with the proof. So in some sense, the old PCP was dot products with the unit vectors, because you're querying just one location. Here you are allowed to query, you're only allowed to query, all your queries should be dot products with the proof. So this subsumes the previous thing. The number of queries you are asked to ask is still a constant, but you're allowed to ask. So in particular, you can ask very, very non-sparse queries this way. So you're weakening the model considerably for the system. If you're allowing non-sparse queries, but every query has to be a linear query. And at least for the cryptographic applications, Ishai noticed that this is sufficient. If you had such a scheme, it was sufficient. You didn't need the full power of the PCP.
What was the field there again?
There's some underlying field you're working over in which the proof is written. This could be GF2 also. I can't say GF2 given what the number is written there. These are not my slides.
Support of the queries could be large.
The support of the queries could be large. So what I'm asking is, there is a proof out there. Give me the dot product of the proof with this string. And the proof, you will get the answer A1. Now I ask dot product of the proof with this answer, with this string, and it will give you the answer A2. And based on the answers A1, A2, A3, and the original string that you had, based on all of these, you decide to either accept or reject.
Parity.
So you are asking parity queries.
But this is also, if you have enough communication to send a query, you can use it the other way, just send the proof.
If you had enough communication, yeah. The point is, so there is the PCP, and then there is how you go use it in the cryptographic thing. Things become succinct. I will not talk about that part. They said that if I construct such a PCP, linear PCP, then they were able to construct more succinct cryptographic. I'm not going to go into how they from this how they construct succinct PCPs, succinct documents. They are not going to send this entire query across.
Okay.
Yeah. What I want to say is, this is not a completely new thing. Sir, notice that it is a relaxation of the PCP, classical PCP, because you are asking a richer set of queries. By the way, you should notice that this is actually the original proof of the PCP theorem. People who have seen the PCP theorem, there is a Hadamard based linear PCP, in which you actually ask linear queries dot products, and that led to an exponentially you gave every possible dot product, you gave it as a proof location. If you didn't do that, if you're just going to ask linear set of queries, you could have just, then it was a quadratic. You could actually give you just, the proof was just this, something like the original witness and the witness tensored with itself. For those who know it, the original PCP proof of the PCP theorem itself had such a linear PCP. It was not called linear PCP then, but it was now out there. It had soundness error order 1 over f with order 1 queries. If anyone of you have taken my PCP course, we have actually done a full proof of this particular construction of this object. And the fact that the soundness is so low actually is something which is useful in the cryptography. You can reuse this process again and again. You can make the field size large and have reusable soundness. This is something which is useful for the cryptographic applications. But this is, notice that this is quadratic in size. It was subsequently observed by Gennaro, Gentry and others that you can, if you are interested only in linear PCPs, you can come up with a linear sized proof. And they were able to do this. And in fact, linear sized PCP with constant number of queries. Then it was later on observed by, forgotten who are the authors over here, show that any classical PCP can be converted into a one query linear PCP. Now, you are saying it's a linear PCP in which you are asking dot products, but just exactly one query. You're not 2 queries, 3 queries. You can actually do this. This was shown by these people. The problem is, though they could show that you get length PCP, the reason for doing all of this was to avoid the PCP theorem. Now, you don't want to use the PCP theorem and to construct an LPCP. Was to bypass. Yeah.
I don't know if I'm sort of. So in the standard PCP thing, when you're making constantly many queries, I mean the amount of random bits that the verifier is going to use directly relates to how long the proof is. In some sense, right?
Yes.
If I'm using order log n queries, then the proof can only be polynomially long.
Yes.
But here, from the random bits of the verifier's point of view, the query chosen by the verifier already seems to have something like.
Yeah, I'm going to still restrict the number of randomness to be only log n.
Okay.
We are going to still keep the randomness to be log n. There we didn't have to mention it in the classical proof.
Yeah.
Here we'll still ensure that the number of queries is still log n.
Oh.
Number of randomness is log n.
Okay. So there are polynomially many different dot products I could ask.
I could ask, yes.
I will pick a few of them and my acceptance criteria after I receive these dot products, that can be anything.
That could be anything. In fact, it has to be non-linear because otherwise everything put together is just a linear system and there's nothing to solve.
Yes. In terms of hardness for props, we're just saying that like 1 minus 1 by f approx is hardened to the n time assuming ETH.
If you had one PCP, yes. If you had a one query thing,
I see.
Only if you have a one query thing, then you can add the logarithmic assumption that Prasad just asked, then you can put every dot product as one single. So immediately you get the MAX-LIN statement this way. MAX-LIN you do get, if you had a one query linear PCP, then you get, and the randomness is only logarithmic. Then putting whatever you say will actually show you that MAX-LIN is hard to approximate.
By the way, this randomness logarithm that should follow by numerous skills, no?
That should follow by?
I mean, what's the length of your?
The proof length is polynomially long.
So then what are log n should?
No, but the number of queries into them, you can ask every possible linear query. No, that's exponential in the.
But you won't need that. I mean, you can simulate it always by using order log n.
How do I know that?
Oh, because if you had non-uniform, right?
Yeah, right.
Non-uniform. I don't. No, but it's something like Newman-like theorem, no? Because I mean, you can always amplify it, and then you can just say that only I ever need to.
Actually, that is true. That is true.
So you can
Yeah, so you can always do that. You can always do that. In communication complexity, you can always reduce the. This is the communication complexity, but this one you can always reduce the randomness to log n. You don't need
unless the proof length is.
The proof length is only polynomial. Yeah. Let's bypass. Let's skip this. Let's just take it for something that's built into the statement. Okay.
But also classical PCP is just an XOR query, right? So it's already a linear PCP.
No. It's an XOR predicate. The query is just you're proving some location.
Yeah, but you just take the, so if you want to try locations A1, A2, A3, you.
So if you had used Harsha's MAX-LIN reduction, then it is in fact it is a 3 query. It gives you an LPCP in that sense.
Yeah.
If you use the gap reduction from 3 sat to max any of the MAX-LIN max-3-lin or max-5-lin statement, that will immediately give you an LPC. But that has the same problem as this, because I'm using the full power of the PCP theorem. I want to bypass the PCP. I want to ask if that will never give me n poly, will never give me linear size proofs, because I'll have it in the heart of it is the proof of the PCP theorem. So PCPs will be at least n polylog n bar. What we want is to do this whole thing, because what we want of the succinct systems is weaker. Can I bypass the PCP theorem in order to? In fact, if I have time, we'll see the full proof of these sort of objects I'm going to. Okay. And in fact, these linear PCPs did give rise to a whole bunch of other succinct arguments. There were several other proof systems called Pepper, Pinocchio, which also run on these blockchains and stuff, which use these linear PCPs to construct better crypto systems, better succinct arguments protocols. Then a subsequent work asked if you can, due to Dan Monet, Boyle, and others, asked, do you really, if you look at this PCP, this one, it looked at the question, based on the problem at hand, it then created a bunch of queries and got answers to those dot product of those queries with the proof, and then ran a predicate on this entire X, A1, A2, and accepted. Now, what I'm going to do is, if people who are familiar with PCPs of proximity, let's say that you don't have access to even the input. You're asked to generate the queries without looking at the input, but the dot product is going to extend over the input also. So if you want to access the input, it should be via parts of the dot product. So it's like, what are PCPs of proximity to PCPs? If the comment doesn't make sense, just think that you're not, the only way you can access the input itself is also by a query mechanism. And they said, can you do this? This was called a fully linear PCP, somehow useful when you're composing systems. This was the reason why PCPs of proximity were also introduced for composition. So cryptographic systems, it was nicer to have this object rather than just linear PCPs for purpose of composition, and this was introduced one, and they showed that this is meaningful even for simple languages, and even if P is not NP. In fact, it is implicit in the results of Aronson and Wigderson and several streaming results. They do have such sort of things, and it's not hard to show that most linear PCPs can be easily converted to fully linear PCPs. And in fact, these gave rise to succinct proofs, not in the distributed C world also. That is, now the input is spread across several parties. You could use these fully linear PCPs to do some protocols. So what we will do is I'm going to push it to the very extreme, this model. Going to ask fully linear PCP, in sense the only way you can access the input and the proof is by asking a query, and ask only one single query. What does this model give us? It seems as if I'm pushing it, asking too much. The reason I'm going to ask it is actually we will be able to construct such objects, and it makes, in that sense, it will give us a positive result stronger. Use more crypto applications. You'll see it makes defining this even stronger object makes the life easier, and we get better results. We get a whole bunch. Okay, so I'll formally define this. So what we are now going to actually ask, I'm going to push this requirement, and so we are relaxed. So there's both a relaxation and a strengthening of the classical PCP model. The classical PCP model, you get to query a constant number of locations in the proof. Here, you don't get to query, you get to ask dot products of the proof with this one, but you get to ask only one dot product. In classical PCPs, if you do anything less than 2 queries, over the Boolean alphabet, you need to make at least 3 queries. For a non-Boolean alphabet, 2 queries suffice, but you need to do at least 2. And here, we're going to, because we're changing the query access, it's conceivable that you can do it with 1. And what we'll in fact show that we will construct DPPs in which you can do it with exactly 1 query. For every language in NP, we'll actually construct a 1 query fully linear piece. I'll formally define this, but this should not be very surprising. The fact that such an object exists. It exists with the parameters that we have, we'll come to it later. For example, let's look at the same coloring question. I'm going to give you an example of a 1 query linear PCP, not necessarily fully linear PCP. Remember the coloring example I gave you. I told you you can do an NP. The PCP theorem told you there's a reduction from 3-sat to a graph, so that if the original 3-sat was satisfiable, the graph is perfectly 3-colorable. if the original tree set was not satisfiable, at least 1/100th fraction of the edges are violated for every 3 coloring of the graph. That's what the PCP theorem told you. Now suppose I give you as proof of the tree set, I give you a 3 coloring. And then what is the linear query I'm going to make? I'll pick a random edge, put 1 at one of the endpoints and -1 at the other endpoint, and query this particular vector. So if it was a valid 3 coloring, this dot product will turn out to be non-zero. If it is not a valid 3 coloring, for the edges which are not colored properly, you will get 0. So this tells you that one query linear PCPs do exist. But this uses the power of the PCP theorem. So it will be at least. So what we want to know is, to prove such a thing, can I bypass the PCP theorem and show that one query linear PCPs? The fact that one query linear PCPs exist is immediately follows from the PCP theorem because of the example I just said. What we want to ask, do we need the power of the PCP? The thing about the example I said, it was not just a one query linear PCP, it was a one query sparse linear. That we will not be able to. The other queries which we will construct will actually be very dense queries. Okay. Okay. So we will now. So that's the whole thing. So the input is there, the proof is there, and I'm going to ask one dot product, an answer, and based on the answer, we're going to come up with this. And two byproducts, we will change the proof system. Byproduct of this, we're immediately going to get ETH hardness for MAX-LIN, and we'll get even better succinctness than was known before for the proof systems.
Just curious, did we have to wanted the access to the input, or the access to the input had to be thought about in this manner in order to conclude the ETH hardness for MAX-LIN?
No, for the ETH hardness for MAX-LIN. So what it will give you is this fact that we made it fully. To get the ETH hardness for MAX-LIN, you don't need this fully linear system. Just the linear thing would have sufficed. What does fully linear tell you? That is the reduction. So what's the MAX-LIN instance? It is a solving system of the form AX equals B. Now, notice the A part just depends on the queries. It doesn't depend on the input X. The X part, the B part is, so it says I could give you the A part, you could stare at it for infinite amount of time, and then I give you the B part. So it's MAX-LIN is NP hard, is going to be ETH gap MAX-LIN is going to be ETH hard even under pre-processing. That's what the fully linear will give you. Without the linear, it will just tell you gap MAX-LIN is ETH gap hard. Now with this, it will give you that it is even with the extra pre-processing, it is hard. Because you get to stare at the matrix A, and that will not help you at all to solve this. But let's ignore that for one. So what's the definition of the model? So we can't call it IPP because I think the name was in inner product proofs, the name was IPP, the acronym is already taken. So that's the reason for calling it dot product proofs. And I prefer dot product proofs. We're working on finite fields, it's not an inner product. It's just a dot product in some sense. So DPP, what's a DPP? For some language L, you're fixing a language, you're looking at inputs of length M and proofs of length M. It's a verifier that is going to, on input, it's going to toss some coins, come up with queries over Fn plus M. And it has, and also builds an acceptance set. That's the acceptance things. If X is in the language, then there exists one proof such that no matter which query and acceptance predicate it builds in, the dot product of that query with the string concatenated, the proof input and proof concatenated will always lie in the accepted string with at least probability C. Usually C is 1 if you have perfect completeness. And in the soundness case, if the string is not in the language, no matter which proof you give me, this dot product, the probability that the dot product is in the accepted set will be at most S. That's the usual definition of PCPs, except I change the query mechanism. Now you have only access it through, you access the proof only via dot products of the particular. So that's the entire system. Notice that this makes sense even for every finite language. This is an information theoretic sort of statement. There's no computation. We can ask, are there DPPs for every language? As I showed you, they do exist. And our main result, we ask for perfect completeness and and by default, we require A to be greater than 1, because if A is equal to 1, then this is a linear system. And linear system, it can't be a linear system. The entire thing can't be a linear system, because then you can solve it using Gaussian elimination. So A will necessarily be a set of size more than 1.
I didn't follow that. I mean, what if you can solve it by
Then checking whether the thing is satisfied or not can be checked using. We don't expect to construct DPPs for all of NP.
Oh, you're saying we can't expect.
If I construct DPPs for every language in NP, you can't expect A to be of size 1.
Right.
Yeah. So that's the definition. So all of the time, trying to show this. Any questions on the definition of a model? It's a new proof system, and this is how. Okay.
And we are going to try and do this with m equals order n.
M equals order n. Yeah. So our goal is to be can come up with DPP constructions which are more simpler than the PCP for the basic PCP. And hopefully we're going to get new parameters which are better than known constructions of the PCP theorem. Yeah.
And what should I think of as f? Should I think of f as a like a constant size field or
There are two theorems.
sure.
Yeah. So this is what we will prove. We will prove that for small fields, we think of field as, right now I said it for greater than 2. So GF3 onwards, I'll state what it is for GF2. For every small size field, so think of some GF3 or GF5, we'll show that for every arithmetic circuit C of size S has a DPP for this associated language. Checking if there is the input can be extended to a satisfying assignment. And what is the proof length? The proof length is linear. It's exactly the size of the circuit times a poly P. So it's linear in the. So I'm assuming P is it's a field of constant size, so GF3 or GF5. We'll show that the proof length is constant. The soundness is just order 1 over square root P. And the randomness complexity is log S plus poly. So these are things which we are able to achieve with the DPP result. We don't know how to achieve similar parameters in the PCP world, in the standard PCP model. By changing the query axis, we managed to get this. Okay. And it has perfect completeness. Perfect completeness. I want to say something. If you want to have for P equals, let me leave it at this. Notice the one problem with this doesn't extend to large fields because then the size of the proof becomes larger. So we have a different result for the large fields. So once the field is large, now I can expect why do I want field to be large? Eventually I want for cryptographic applications, you want the soundness error to go as small as possible. You don't want it to be stopped at this one soundness error will be only 1 over square root P, which is now a fixed constant. I want it to go arbitrarily small. So now set we now would ask, this one doesn't get me arbitrarily low soundness error, but whereas this one will do. If I say I want soundness error epsilon, then there exists a DPP over a prime field of order poly S times 1 over epsilon. The field I'm considering is very large. It's polynomial in the size of the circuit and in 1 over epsilon. But the proof length is just 2S. It's a fixed 2S field, but field elements. So each thing is log P length. Soundness error epsilon. Forget about what we
are. I'd like some help answering this.
Yes.
Like I want to understand it like more in the language that you introduced so far.
Yeah.
Where this classic PCP language is arithmetic circuits language is a bit of.
No, sir. That's just you can ignore that. That is just for it is just stating for which problem for SAT or graph coloring. That is. I'm looking at the problem. The reason I mentioned arithmetic circuit is I have to work with a finite field. So the underlying problem should be an arithmetic circuit rather than a Boolean circuit. So that's why I'm doing it. But you can do reduction for it. Think of it as any problem because we will soon see that any problem in NP can be reduced to such a problem. So think of it as any problem in NP for which there's a circuit of size S. The testable circuit, checking membership in that is of size S. Then it has these parameters. If the testing membership has this one, that is the NP. If a language is in n time T of n, then replace S with T and you'll get all of these.
And the proof that does not incur any blow-ups.
The proof length will incur. The reason I'm telling you this is at its specific languages, if you take an arbitrary language, you have to reduce it to arithmetic circuit, and that reduction involves Cook-Levin.
Nice.
That will involve an n log n. The reason I have to state it this way is I don't want to put that log n, so I have to specify which language I'm talking about. Otherwise, just a simple application of Cook-Levin is going to have, I don't know a proof of Cook-Levin which doesn't have the log n over it. Therefore, I have to specify the particular, I can't say for every language in L. I have to specify which language in L. In every language in NP, I can't state this. I have to specify which language, and I specify the most general language. Checking membership I give you a arithmetic circuit and ask, is there a string that makes the circuit go to 1? Any questions? All comments I have here. Yes, yeah, that's and the application is for the small field, we'll get an ETH up. We'll get that it's ETH hard to approximate max-LIN to some factor. And the proof is, because the previous proof bypasses the BCP theorem, the construction DPP, this will be a simpler proof of this statement for the proof of BCP theorem. And this is a rare example of a ETH hardness of approximation. We have not been able to. There was a recent parallel to this work, the work by Gulswami et al. In the parameterized complexity work. Actually, Saket spoke about this when he gave a talk a few months ago. That's the only other place in which we have seen a similar hardness in the approximation world based on ETH. Okay? But one thing should be mentioned, the usual NP hardness approximation for max-LIN is typically 1 over P versus 1 minus epsilon. So the soundness vanishes as P goes to infinity. Our things don't get that. It doesn't vanish with P. It's some fixed constant 0.99 and I don't know how to reduce that. So that's an advantage of the PCB machine. We know that. In the large field things are basic. The motivation was for getting some succinct arguments with shorter proofs. So they do get you shorter proofs and faster verifiers. We don't know where these numbers come from. These have been done in practice on some of those ones. But they still have some disadvantages. If you, this one I'll skip. I want to show this time. This I have about 10 minutes. I'll try to say something on the proof of this. Questions?
You mentioned that A cannot have to be a singleton.
Yes.
How large does it have to be?
So it will be 2. It can't be 1, it will be 2, and that's what we do. Yeah. So how do we construct such a thing? So what we do is we'll first construct not a DPP. DPP is a single query object. We'll construct an object which has more than one query. Say 4 queries or 5 queries for the arithmetic circuit set problem, and it will be linear proof size. And then we'll construct an inner DPP for a fixed language. And what's the language? It's just that language, the 4 queries, you're going to check. There's a 4 query thing and an acceptance predicated. Just for that particular language, I'm going to construct a DPP. It's a constant size language. Everything is constant over here. So I can spend as much amount of randomness or anything over here at this point. It's a constant size problem. So I can do that. And we'll show that this just the standard composition that we have done in all language of PCPs actually works extremely well. In fact, it's much cleaner than standard PCPs. You just compose this object with this because it's a fully linear PCP, you can just transfer it to an inner PCP and everything works. You will get the small field. That's exactly what we do. So our job is to construct these 2 objects. And the proof for this one will be the proof for the outer object. And the proof for every randomness of the outer object, we have a particular 4 query thing. For each of them, we give the inner PCP's proof. The proof is just the concatenation of all these proofs, which is exactly how it was in PCP composition. Proof is the same. So the proof construction of this object is exactly similar to PCP composition, but the proof that this composition works is much, much simpler than the proof of PCP composition. Because it's a linear query, there's another linear query. Instead of doing this linear query, you do that linear query. And this will give us this. How do we construct this object? I'll show you this. The outer F piece. This was actually implicit in past construction. What our construction is just going to simplify and generalize several earlier construction. These construct because in the process of simplifying generalization, we managed to get linear size. The past construction did not get it. And our key tool will be what the result from coding theory is called multiplication codes. We'll say a code has a code E. So E is some encoding from k bits to n bits. We'll say it's a multiplication code with respect to another code E star from a different set of Fk star to Fn. There are two codes, or both on the same file. The code words live in the same space. Both this is an Fn, that's an Fn. We'll say this code is a multiplication code. If you take any two code words in this code and take element-wise product. So C star is take element-wise product. So every coordinate take coordinate-wise product. The coordinate-wise product, whatever string you get, should be an element of the other code word. Notice that all Reed-Solomon code has this. If E was Reed-Solomon codes of degree D, and E star was Reed-Solomon codes of degree 2D, then you would just get this. So almost all the algebraic codes have this flavor. They have this multiplication property. We want such codes in which both E and E star have a good relative distance on them, and the useful instances to know are Reed-Solomon and algebraic geometry codes. So all of them, anything which has the codes are defined by a degree parameter, we will have such things. We will use algebraic geometry codes because we have constant rate codes which have this feature. That's what we're going to use. Instruction. And because they are linear constructs, they'll be linear and systematic, these codes. So,
Reed-Solomon also has that.
Which one?
Constant rate.
No, sorry. Why do I want it? Over a constant size alphabet.
Oh, you want it over a constant?
Because I'm going over, I want to do it over some constant size alphabet. I want it over constant size. Reed-Solomon, the alphabet has to go large. I'm going to know. So we're going to talk about this particular problem, which is sort of related. So I've given three matrices ABC. The input is X. I want to check that this matrix X has this property that AX, look at the vector AX, take its coordinate-wise product with, or what's called the Hadamard product, with the vector BX. Is it actually CX? This is what I want to ask. This happens to be what called rank 1 constraint satisfaction problem. This happens to be the heart of all of these cryptographic systems. It's powerful enough to capture all NP-complete problems because there's a quadratic constraint over here. This is a quadratic constraint, multiplication. The xi, xj, they are getting multiplied over here. I want to check that this is, I give you ABC, I want to check X has this property without querying all of X. And it is known that if I construct a fully linear PCP for this particular problem, it gives you a PCP for this problem without any extra blow up. Let's ignore that. And how am I going to give an FL PCP? So I have this. What I'm going to give you as proof is not, so because if AX is let's look at AX, let's encode it using the first encoding. Encode BX using this one and take their Hadamard product. That we know is because of the property of multiplication codes, that we know is the encoding of some other string E star n. The proof is going to be that n. I'm just going to give you that proof. That as a proof. The proof vector is this m. Notice everything is linear over here. That's all is the proof.
So the code needs to be a linear code that has these properties.
Yes, a linear code that has this property. And we'll use some AG code for this. AG codes are linear. And what does the verifier need to check? The verifier needs to check that the m proof given here indeed satisfies the above equation. And furthermore, Cx, the first m1 bits of Cx, or the first m1 bits of m is actually Cx. Because it's a systematic code. We want to check Ax star equals Bx star. So first we want to check that this m is actually the encoding got this way, but furthermore we need to put Cx. So because it's systematic, the first M1 bits are actually CX. We need to check these two properties we have done.
I do understand item 1, but item 2, CX, I guess
No, I could have just given something which is not CX. There's nowhere else C is being brought in the item 1, no? I need to check that AX star BX is equal to CX. How do I check that? The item 1 is not, doesn't involve C at all. It just says AX star BX is some code word of E star M. That's all item 1 is checking. That E star M I want to check is actually the encoding of CX. That M is the encoding of CX is what I need to check. I want to claim that's the entire proof. Choose a random bit in the n locations. Check E star. The ith bit of E star Mi is actually EAXI, the ith bit of this, and the encoding of CX minus 1, the ith bit of it is 1. All of these are linear in the inputs. So you can just run all of these queries. There are 4 queries. You're making one query here, one query here, one query. There are 4 queries. These are all linear. You just run them all, and the distance of the code will give you, it's a fully linear piece.
So we wanted to check if AX star BX is equal to CX.
Yes.
So we are instead going to check if that.
I'm going to give you, so instead of CX, I'm going to give you the encoding of CX according to E star. I'll do that in a couple of minutes. I'm going to give you the encoding of CX according to E star.
M is supposed to be CX, is that?
Huh? No, M is not CX. Sorry. What am I? Yeah.
So M is supposed to be the
Sorry, I'm making a mistake over here. M is supposed to be CX itself. M is supposed to be CX.
Yeah. Okay.
Yeah. M is supposed to be CX itself. There is no M1 plus K bits.
So the proof vector is E star M. Or no.
Proof vector is M. Proof vector is this thing which I'm claiming is CX. I want to claim, I give you a vector M which is supposed to be CX.
So firstly check if M satisfies the equation that.
First I check that M satisfies that equation. And then I check actually the M given is actually CX. Okay.
I think what you've written is right, but
You will have it there at the very end. So this, and there are 4 queries here. I have access to M, so I can make E star M. I have access to X in the input, so I can get E of AXI. This composition of 2 linear operations, I think that's a linear query on the input. That's a linear query on the other input, and then all of these are linear queries. You can do it. It's 4 queries, and the distance of the codes is a proof of it. The distance will give you it's a fully linear piece. So the outer object is just that. You have AG codes, and you get this. You actually get like this. I will skip all of this. I'll skip the inner DPCP. Just say 1. Actually, let me skip the inner DPCP. And there is easy way to construct this. So yeah, we put these two together, you get object, and then gives you skip this. It should be clear the hardness of approximation. Once you have a DPP with one query PCP, one query linear PCP, it immediately gives you hardness of approximation of max-LIN. Yeah, and just conclude what we had. We came up with a new type of proof system. It's an extremely simple verification. It's a single linear query. That's the main advantage of it. And because we relaxed the query mechanism, we were able to construct proof systems which are of linear length. And we had 2 different constructions. One was small fields and another were large fields. Application, we got an application to ETH hardness for max-LIN. Notice we have sacrificed the locality over here. And the fact that we're able to come up with such a simple proof tells you how powerful locality is. The locality, that's what gives the PCP the entire strength. You're able to prove things for KCSPs, where K is 3 or 5. If you bypass that, I can give you potentially a proof which I can explain in half an hour.
But in your K would be still like log n, which is still better than like n.
Yeah, but our case over here will be linear in n. I don't know how to control this.
PCP should have been called NCP.
Yeah, they should have been called locally checkable proofs. The heart of them is the locality. Key is locality over there. They should not have. Some open questions can we come up with? So one query LPCP, we don't know it's 1 over Q soundness, we only know it's 1 over square root Q. To get 1 over Q, you have to go to the PCP theorem. Can you bypass the PCP theorem to get this? Yeah. No, it's not focus.
Okay, so the PCP theorem just a linear size. PCP theorem in general tells you that NP hardness of stack gives you NP hardness of gap stack. Okay. And now if you have a linear size PCP, then it would have told you that ETH for stack goes to ETH for gap stack.
Rather, it shows you that gap problem also, that is asking.
It may not be SAT. Okay, gap something.
Gap something which can be made to 3 SAT. Those reductions are always nearly linear. Always linear. The standard reductions which exist in your Sipser's textbook are all linear in time.
So now I was just wondering if there is an SETH analog of this, which is that, you want to say that as the arity keeps increasing, you want to basically say there isn't anything better than 2 to the n that you can do.
Yeah, so but our reduction in so we don't have an SET which analog of this. The reduction essentially gives up on the locality. Those things.
SEP is just reduction for max-LIN.
Yeah, I was just wondering, in the sense that since now the locality is large, can you make a statement of the form?
We are not able to control the locality in our proof. It's something that comes up with these guys. I don't know how local they think. And essentially, you're using error correcting codes. So
So even quantum factors start to become problematic.
Yeah.
Is max-LIN ought to be as hard as
I don't know. One of the facts we received in the paper is why is max-LIN? Why is this version of max-LIN even considered a hard problem?
yeah.
The only reason I know is I don't know an algorithm. You say it's not a hard problem.
It is surprised.
It will be surprising. I don't know of a reduction, but all the known proofs of the hardness goes via. No. We don't know all the proof of. Question is it easier? Is the hardness easier to prove than PCP theorem? That's your question because it's certainly hard. Question: is it easier to prove? I don't know. All known proofs I know go via the PCP theorem. This is the first instance where I bypass the PCP theorem. Yeah, it's a valid question, and what we essentially show is yes, it's a positive answer to your question that max-LIN, it's a simpler problem. If you're weakening the arity, it's a much simpler problem than max-LIN it's easier to prove the hardness than max-3-LIN. Yeah, which is in some sense the takeaway of the result. Yeah.
More questions?
There are some more that's for you.
Save the slides safely. You should save the slides safely.